the limits, the one-sided limit, and the continuity. So in order to understand the idea, let's imagine we have a circle and an inscribed triangle, and then we increase the number of sides of that polygon inscribed in the circle to become a square, and then increasing it to a pentagon, and so on. As much as we increase the number of sides, this polygon tends to be exactly equal and coincide to the circle. So we can say that as the number increase of the sides for the n-gon or for that polygon, it will be equal to the circle. In other words, the function 1 over x. Now we have dealt with the function 1 over x several times, the basic rational function. At x equals 0, we all know that at x equals 0, this function is undefined. So if we need to say f of 0 for the 1 over 0, substituting the x by 0, this will be equal to undefined. And here comes the very powerful tool called the limit. The limit does something else. It says, okay, we cannot read the corresponding y at that x equals 0. This function is undefined. But what the limit would do, it would approach that 0. I know that you know the graph of it. Here is the graph, and that's the part of the 0. So the limit will try to approach x equals 0 in the x-axis. For example, taking x by 0.5 and then 0.4, 0.3, trying to approach the 0. So it will start by 0.5, 0.4, 0.3, 0.2, approaching the 0, right? And it will commute the corresponding f of x to read the corresponding y. Each time, one may notice that the function would increase. The function is increasing because these are small numbers set to the denominator. So the value of the function is getting to increase and without limit. So the limit says that the limit tool or operator, if we can imagine it, would tell us that as x is approaching 0, because that's what exactly the limit did, the function f of x is approaching a very big number, or is increasing. And it's increasing without limits because we might here try thousands of points. So it's increasing without limit, which we might call infinity. So this is one very powerful situation where the limit is telling us the limit of the function, if it exists or if it does not exist. Like here, the infinity, there is no limit, but like we will see later, here, for example, that table, it tests as x increasing for 1 over x. So as x is increasing, if we say at that direction, x is increasing from 1 to 2 to 4, and the corresponding f of x here, which is 1 over x, you will see that the corresponding y's is decreasing, 1 to 0.5, 0.2, 0.1, 0.01, and so on. So in that direction, the y corresponding is decreasing while increasing the x-axis, and it's decreasing and approaching a certain value. So in this situation as well, the limit can tell us as x is increasing, which means we can approach a very big number. We always sign it with the infinity. Like when we see someone beautiful, we say that is a beautiful person. So it's like a sign. X is approaching a very big number, which we can call infinity. At that case, the function 1 over x is approaching which value here? This value that we are approaching here is the 0. So now this is what the limit does. Simply, f of x gets closer to some limits. As x gets close to some value. So as x here is getting close to a certain value in the x-axis, the f of x, in the other hand, will be approaching another value, and this value we will call L, or the limit, denoting it by the first three letters of the word lim, and then we will write here the f of x as x approaching that value a. This will give us the L that we are seeking. Let's consider the function that we can see here. It's x squared minus 1 over x minus 1. If we want to work it at x equals 1, which means that we will substitute x by 1. So here we will take an example for the f of x equals x squared minus 1 over x minus 1. If we evaluate it at x equals 1, this will be 1 squared minus 1, which is 0, over 1 minus 1, which is 0. And the 0 over 0 is an indeterminate value. Right? So it's, or simply you can say undefined, but actually it's not undefined, it's indeterminate, because we differentiate between two types of values in mathematics: the undefined, which we were not, or the mathematicians were not able to find its value yet. However, the indeterminate, the values that they call indeterminate, are values that they were able to evaluate and commute by different ways, not by a direct way like reading corresponding y for a specific x, but in other ways. Let's now see what would the limit do if we take the limit of the same function as x approaching now. Now we don't want the f of x at x equal 1. We want the f of x as x approaching 1. And of course, our first approach will be by direct substitution. And direct substituting here will give us the 0 over 0. And this value is indeterminate, so we try to work it in an indirect way. And here we can see all that we have x squared minus 1, which is a perfect square. And we know that x squared minus 1 got a simpler equivalent, which is x minus 1 times x plus 1. So we might substitute it and simplify it. Now we are factorizing to take the limit of, instead of x squared minus 1, we will write it simplified. Why? Because it's a more simple equivalent form for that function, which might help us to find the solution we are seeking. So here, after rewriting it, it's obvious that we can simplify these two factors together in order to be left with only one factor, which is x plus 1, as x approaching 1. And now, after the simplification and cancellation that we did, we simplified, then we cancelled, right? Or we factorized, then we cancelled. And the last step will be that we will give it another try. After this cancellation, we will give it another try with the limit substituting x by 1, and here it will be equal to 2. So what we did now is solving the limit problem algebraically. Sometimes it was solved by graph, so we might graph this function and try to see what the f of x is approaching, what's the height at x approaching 1, and it will be 2. And sometimes it's solved numerically. What we did now is algebraically. It can be solved graphically. From the graph we can read the corresponding y, and finally it can be found numerically in tables, like we have the table here. So that was the value of the function itself, and here is the table approaching the 1, starting with 0.5, 0.9, 0.99, and so on. These numbers are approaching the 1. The function was approaching what? 1.5, 1.9, 1.99, and so on. So it seems that it's approaching 2. And this is how we write it. The limit of that function as x approaches 1 is 2. And mathematically, we will write it simply with the LIM, the limit, and the function as x approaching 1 is equal to the capital L value that we are seeking, which is the 2. Okay. Now let's go to the worksheet in order to solve some of our problems algebraically, because this will be our task to get it algebraically or graphically. And about the numeric solution, that was before, so we won't do it numerically anymore. So our first approach, like we said, will be always to direct substitute. So let's start by direct substituting here. It's the limit of that function 3x plus 2 for x is approaching -3. We will direct substitute to find its 3. If we are direct substituting, we don't have to write the template of lim and x is approaching. This only happens when we direct substitute. So substituting the x with the -3, that's -9 plus 2. That's -7. So the value here is defined. Let's try here to solve it by direct substituting. X by 2, it's negative, and then the 2 squared plus 2 minus 2. Here we have -4 plus 2, -2. -2 minus 2 is -4, and that's a value. So here we are, that's the value of L we were seeking. Here approaching, x is approaching 4, and direct substituting as well. We will have 4 plus 4, which is 8, under the cube root, which gives us 2, and that's the value that we are seeking for the limit. It seems that the function corresponding to x approaching 4 is approaching 2. Again, here in part D, we will direct substitute to find x, substituting x by -2 plus 1 over, we have here 2 minus 2, so that's -6 plus 1, which is -5, over 2 minus -2, which is 2 plus 2. We can turn it into 4, and this is the limit value which is accepted. Moving to number E with a direct substitution, substituting x by 5 plus 4 under the root -2 over the x, which is 5. So here we have 9, the square root of 9 is 3 minus 2, which is 1 over 5, and here is the value. Here in this exercise, let's again substitute. So always remember to direct substitute. This is your first approach in solving any limit problem. Whatever what you can see, you have to start by direct substituting. Sorry, I need to replace this x by -1. So we have the -1 plus 1. In the numerator, we have -1 squared, which is 1, minus 1, 0, over -1 plus 1, which is 0. Oh, we got an indeterminate value, which we can work around it by simplifying that given function. And yes, there is a factor here that can be simplified. It's the perfect square of x minus 1 times x plus 1. And we got to remember and recall the perfect square. When it's x squared minus a squared, this is equal to x minus a times x plus a, right? And if we have the x cubed minus a cubed, that's the difference between perfect cubes. We have a small bracket that looks like that one, and another, instead of that bracket with the addition, we have another bigger bracket. So we have in the power of 3 in the perfect cube, we have a small bracket and a big bracket. After writing the small bracket, which is one of each, we can take 2 of the first times the second with the opposite sign, and finally the last with the positive sign. So now if that was an addition, we would have another expansion with the plus. This always carry the same sign as here. And then here we have an opposite sign. So if it's positive, it's going to be negative, opposite sign. And this sign is always positive. If you put these letters together, you'll get the word soap. And this is how you can memorize it. So let's here simplify what we are able to do, simplifying this x squared. So I'll write lim, because now I'm simplifying and I'm still using the x. So I have to write this template. X is a limit of x approaching -1 for that function, which is simplified and expanded like this. And now it's obvious that we can simplify the factor x plus 1 with the x plus 1, and we will be left with one factor, which is x minus 1, as x is approaching -1. So here it's going to be, instead of x is the -1, minus 1, which is -2. So here we go, we found the value that we seek for the capital L after the simplification we did and the cancellation. Now let's try number G. Number G will be also by direct substitution 0/0, and we will try to simplify or factorize this denominator term in order to have the limit of t minus 5 over t minus 5 multiplied by what? T plus 5, as t is approaching the 5. And we can see also here simply that we can factorize these two terms and direct substituting by t equal 5 in order to get the value, which is 10. And here we go. In number H, we can also start by direct substituting, where we will find the value is 0/0. And still we can figure out that there is a factor that can be factorized here, which is in the numerator. So we can say that this would be equivalent to the limit of, these are the power of 3. So we can see this as x power 3 plus 2 power 3 over x plus 2, as x is approaching -2, right? Now it looks like that expansion. Just apply it. Let's apply it. So here we have the limit of x plus 2. That's the small bracket. And there is another big bracket we have in the denominator x plus 2, and x is approaching -2. Now the bigger bracket is x squared, the first squared, x times 2 with the opposite sign, x times 2 or 2 times x is the 2x with the opposite sign, which is minus, and then the last term here plus 2 squared. Plus 2 squared is plus 4. And here we go. And of course we can observe that these two factors can be simplified out, and that we will be left with an equivalent function, which is x squared minus 2x plus 4, as x is approaching the -2. Now after the cancellation, so first we did the simplification or the factorization, and then we did here the cancellation. So first we did factorization, and then we did cancellation. Finally, we try again to direct substitute. We try again to direct substitute with the x -2. -2 squared is 4. 4 and -2 times -2 is plus 4. So 4 plus 4 is 8. Plus 4 is 12. And here we go. That's the L that we are seeking. Perfect. Let's see number I. By direct substituting here, x by -1, -1 plus 2, that's 1. The square root of 1 is 1, and 1 minus 1 is 0, over -1 plus 1, which is 0. Okay, we got that indeterminate value that we get used to get around it by factorization. Once we factorized the perfect square, another time we factorized the perfect cube. What about here? Yes, here there's another significant thing, which is the square root. This square root, we will be able to deal with it also by canceling it. And we will always be able to cancel the root if we found an indeterminate value while it's involved in the function with multiplying it by its conjugate. Some of you have been introduced to this word before, and it's very simple when we say we have any term plus any other term, its conjugate will be the same two terms. We don't touch the terms, we just alter the sign in between. So if it's positive, it's going to be negative. If it was negative, it will be positive, and that's what we are going to do. So here, what we will do in order to cancel the square root, because they figured out that the square root here is able to be substituted or replaced, and if it's replaced, it will solve the issue. But as I told you, like when we were factorizing, we will factorize and then cancel and back to direct substitute. These are our main three steps here: to factorize, then to factorize, and then we cancel, and finally we again direct substitute. Now we will multiply with the conjugate, cancel, and then direct substitute. So sometimes when we have the 0 over 0, we got either factorize or multiply with the conjugate, which is called rationalize. And then that's in step 1. We do this or that, and in step 2 we cancel or we simplify, and finally we direct substitute. As if these are the main steps for solving the limit problem if the value or the output of the first direct substitution was 0 over 0. So here let's continue this with multiplying with the conjugate, which is the same two terms without touching them, the square root of x plus 2 and 1, and then we will alter the sign in between here from negative to positive. Of course, you know that we can't multiply the numerator only. We have to multiply up and down the numerator and the denominator, so that overall, as if we are multiplying with 1, which means that we didn't do any change for that function. And that is our suitable one here to use in multiplication. Now let's multiply the numerator with the numerator and then the denominator with the denominator, like we do in the normal fraction multiplication, as if we're multiplying 3 over 4 times 1 over 8. This is what we always do. So think of the numerator here, that we have a factor and another factor. How to multiply these two brackets? We take the first times the first, and then the second times the first, and then the second times the second, and finally the first times the second. You may use the FOIL, which says for x minus a times x minus b, it will be the first x squared, the outers negative bx, the inners negative ax, and then the last is the plus ab. Let's multiply here. We will have the square root of x plus 2 times the square root of x plus 2, and this means that we have the x plus 2 under the square root squared. And in this situation, the square root will cancel the squaring, or the squaring will cancel the square root and leave us with the x plus 2. So we will have only x plus 2. Negative times positive is negative, and then 1 times 1 is 1 over. We will keep the two terms of the denominator as they are because we were not seeking to cancel anything in the denominator. And now we will try to simplify. Simplifying what? Here in the numerator, you can see that we have x plus 2 minus 1. So as if we're having x plus 1, right? And in the denominator, we had x plus 1, and then the square root of x plus 2 plus 1. And this is under the limit operator as x approaching negative 1. Now someone will tell me it's very obvious that we know now what to cancel. So now we know what the root did and what we are required to cancel together and simplify the function. We will cancel the x plus 1 with the x plus 1, and then we will be left with only that term in the denominator. And after we multiplied with the conjugate and then we simplified and cancelled, we will try again to direct substitute. So let's direct substitute so we don't have to write the limit, right? Let's now directly substitute the x by negative 1. Here we have negative 1 plus 2, which is 1. The square root of 1 is 1, and 1 plus 1 is 2. So directly we have the value, which is 2. 0 over 0 here is 1/2, while the 0 over 0 above in number h, for example, was 12. In number g, in part g, the 0 over 0 became 1 over 10. So the 0 over 0 is indeterminate value because we can work around it and determine it. Sometimes it's 1 over 10, sometimes it's positive, negative, fraction, whole number. It can be any value according to the function and the point we are addressing. Now we need to consider this exercise. Exercise 2. Let's do like we did before. Direct substitution is our first approach in solving any limit problem. X is approaching 2. 2 minus 2 is 0. Absolute 0 is 0 over 0. Okay, it's indeterminate value. We used to deal with, we first in the limit problem, our solving strategy is to direct substitute. If we have any value, then it's accepted. Any value like 0, 1/2, negative 3 over 4, so negative, positive, whole number, 9, 8, 6, 7, 2, 3, 4. All this big number, it can be the limit problem, yes, solution. However, if we have the 0 over 0, we try the following. First, we try to notice if there is something to be factorized. And we have dealt now with the perfect square and perfect cube. And if we will factorize, we will go to simplify by cancelling. And then once more, we will try to direct substitute. Okay, what if there were none to factorize? We will, for example, have the root in the numerator or the denominator. and we will be rationalizing it or canceling the root by multiplying it with the conjugate. So that's our second scenario, and we will continue the same. Now we don't have something to factorize in this exercise 2 part A, neither something like a root or something to rationalize. What we will do in this case, we will try to recall what we knew before from the behavior of the absolute. You know that the absolute of x minus 2, the absolute of x in general, at the beginning, it's either x when x is bigger than or equals 0. We all know this. Or it gives negative x if x is less than 0. Also, to memorize it once more, that in the x and y plane, if we input to that absolute function, y is equal here to absolute x. If you input 1, the output is 1. If you input 2, the output is 2. If you input 999, the output is 999. As long as it's a positive whole number, it will give you the same. What if we input negative 1? The output will be 1. What if we input negative 2? The output will be 2. So what does it do to the numbers less than 0? Yeah, it just multiply it with negative in order to output a positive, and that constructs the V shape for the absolute. Now let's reflect this work to the absolute of another function which is called x minus 2. The absolute will output x minus 2 if the x minus 2 is bigger than or equal 0, and it will output negative x minus 2 if the x minus 2 is less than 0. Let's simplify this. It seems that it outputs at x minus 2. If x minus 2 is bigger than or equal to 0, then x is what? Yes, we knew from worksheet 1 that we can solve such an inequality by moving the 2 to the other side or by adding to both sides plus 2 to get rid of it. So this will happen if x is bigger than or equal to. And the negative x minus 2 will happen when the x is less than 2. So this is the simplification, and that's what we will exactly use. We will say now that it seems that approaching the function at certain situations from one side, like that person here, he's running up a hill, and then finding the path is magically. There is no continue and there is no rest of the path. So it wasn't obvious for him approaching from one side that there is no continue for that path. He cannot continue in that direction. He didn't figure it out from one side, right? So sometimes we need to test it from both directions to be sure where it should be. Like here. Here we didn't need to do this, but we will see here how shall we do this. Here x is approaching 1, starting by 1.5, 1.1, 1.01, so as if it's approaching it from far away to the right side, and then decreasing the number approaching 1. And at each number here, we evaluate the f of x to find out that it's approaching 2. Now, if we went to the other direction, the numbers smaller than 1, starting with 0.5 and then increasing to the 1 direction, 0.9, 0.99, and so on, approaching the 1, reading the corresponding y or the corresponding function value for these x values, we find that the function is approaching 2 as well. Now we have the full vision from both directions that this function limit as x approaching 1 is equal to 2. Let's consider this different behavior. This is another function at x equal 5 here. If we approach this 5 from the right side, for example 4.5, 4.6, 4.7, we will find that the function is approaching a value which is 3.8. And we will denote this x is approaching 5. We will make it power negative, as if we are coming from the left side, and the left side is always, we know that the negative numbers exist to the left of the 0. This is why they denoted by the power of negative if you are approaching from the left side and the output is 3.8. Approaching from the right side, for example, after the 5 into 5.5 and then back to 5.4, 5.3, 5.2, and with every x at 5.5 we read the function. 5.4 we read the function. 5.1 we read the function. We find the function is approaching 1.3, which means that this is the value of the limit for that function as x approaching a from the right side, and from the right side here is indicated by the power of positive. Now we have two different values approaching the same x from the different sides, and this means that the limit does not exist. As you see here, the function, as if there is a jump that happened for the function, as it was working from the left, increasing for x, and finally at x equal 5 it jumped to the 1.3 and then continue normally. So now when you see the limit, think about approaching, and we will summarize this at the end, but let's move here with the absolute. So here this absolute is one situation where we need to address the one-sided limit. Because it outputs 0 over 0, and only because it outputs 0 over 0. So it's not the case that whenever you see absolute, just go to the one-sided limit. No, only if it outputs 0 over 0, we will say that we have to approach 2 from the right side, and then separately approach 2 from the left side. From the left side, we will take the negative x minus 2 instead of the absolute of x over the same x minus 2. So as if here what we did is substituting the absolute with the second part from the left side, and that is the right side. So here I will remove the absolute x minus 2 and write only absolute and write only x minus 2, because here we are approaching from the right, over the x minus 2. Now after doing that separation or that translation of the absolute, we will try to cancel. If you try to direct substitute again before cancelling, you will get the same result, the 0 over 0. You didn't work around the 0 over 0 yet, unless you simplify that form, that function. You need to cancel factors together to get an equivalent form. So here we will cancel the x minus 2 with the x minus 2, like exactly what we did before. In this case, we will be left with, if x minus 2 is divided x minus 2, this means that we are left with 1. And the limit of constant is constant. There is no x to substitute, right? So the limit of 1 is what? Is 1. It's not going anywhere else. 1 is 1. Its limit is 1, and the function is defined as 1 at that point. Okay, here, what shall we do? Again, we have the same two factors, but we are left with the negative. Yes, I know that you took care of it. So here, when x is approaching 2 from the left side, we are left with negative 1, not 1. And the limit of the constant is constant, so it's negative 1 as well. Finally, what we do is that we test whether the two sides were approaching the same value, or do we have a jump, like the scenario we saw geometrically or graphically. Here we will say that since the limit of x approaching 2 from right for the f of x was unequal to the limit of x approaching 2 from left for the f of x, one was 1 and the other was negative 1, they are unequal. Therefore, the limit of the function as x approaching the full 2 does not exist. Why? Because the function jumps. The function does a jump at x approaching 2 or at x equal 2 from the right side negative 1 to 1. And here, if we direct substitute directly the x equal 2, the function is undefined. Here, at x equal 2, it gave us the 0 over 0. Here. While the limit did find a value here. Here the limit also does not exist. Like before, when the function was failing to read the corresponding y, the limit were able to find the limit of the function. Here the limit does not exist, and the function also does not exist at 2. Okay, so this is the first case where we see that the limit does not exist, and we were able to deal with it, and we decided the limit does not exist because approaching from the two different sides gave two different values, which means that the function got no limit at that value and that it does a jump. Here we need to study the limit of f of s as s is approaching 1, and the f of s is defined as a piecewise function. We have dealt with the piecewise function before, and we know that it divides the number line around that point indicated here, which we call it the joining point. Right? So here, around the 1, the function before the 1 for the numbers less than 1, what's the ruling function? It's s. What about after 1, when s is bigger than 1? For the values here bigger than 1, the ruling function is 1 minus s. Now, if we need to study the limit of the function as s approaching that joining point, this point 1 is the joining point indicated in the function definition, right? So in that case, we can't approach it at once. We will say here that we have to approach s approach 1 from left once and s approach 1 from right another time. From left, which function shall we substitute or write here? And from right, which function shall we study here? I know that someone is telling me now from the left here, 1 to the left, that's the left side. The ruling function is s, so we will write s. And from the right side, when 1 is to the power positive, that's the right side, the ruling function is 1 minus s, so I will write it here. I will substitute the f of s here with s, and here with 1 minus s. Because before the 1, this is the ruling function, so if I want to define values before the 1, this 1 will be the functioning. And if you want to approach 1 from the other side, this other 1 minus s is the ruling or the function here. Now it's very simple limit problem. S is approaching 1. What's the limit of s? Directly substitute, it's 1. And here, if s is approaching 1, what's the limit of 1 minus s? It's 1 minus 1, which is 0. Finally, they are not equal. Therefore, we directly decide that it seems that from the left the function was 1, from the left of x equals 1, the function was approaching 1, but on the right the function is suddenly approaching 0, which is a different value, and it seems that there is a jump, geometric jump that happened here. So what we decide that the limit here does not exist. So that's the case where the limit does not exist. Now let's move to the continuity topic. We have discussed the limits and the one-sided limits, which we needed in two scenarios or in two cases: the absolute, when the function outputs 0 over 0, the direct substitution, or the piecewise function when we were approaching the joining point. So if we were approaching any other point, there is going to be no problem. For example, here before we leave it, let's say that we need to study, instead of limit of s approaching 1, let's approach 10. Now, if s is approaching 10 for that given function, what is the function I'm going to substitute here for f of s? 10 is where 10 is to the right of 1. So 1 minus s is the ruling function. And if we try direct substitute like we do always as the first step solving a limit problem, we will find that it's 1 minus 10, which is negative 9. And it is a value that's accepted. So wherever we find the limit for that piecewise function, it will be defined. Only if we are addressing the joining point where the number line is divided around, we have to test the both directions. Okay. So moving now to the limits, the continuity. Let's wrap up what we do for evaluating the limits. We just put the value in by direct substituting. If we have a value, that's it. If we got a 0 over 0, we need to try something else, which is either factorizing, like here the perfect square, or if it was perfect cube. After factorizing, we will cancel two terms together to simplify and get an equivalent form, and then back to direct substitute, and here we go. We might also try to multiply with the conjugate, which is the two terms as they are. We don't change the signs inside, only the sign in between. Like here, the 2 minus square root of x over 4 minus x, you might try it out by direct substituting x by 4, and you will find that 0 over 0 multiplying with the conjugate, you will get the 4 minus x, which will be simplified with the 4 minus x in the denominator, left with that formula where we direct substitute it to become 1 over 4. Here for the continuity, let's consider these four graphs. The first graph is continuing and there is no any problem found. So we call such a function a continuous function. Because there is no anything noticed, the function is running smooth and continuous. And we find also an observation that if we substituted the function at any x value here in the x-axis, we will read the function. And if we found the limit for f of x at any x approaching any point, we will find the same value. So f of a is equal to the limit of x approaching a for f of x. And this is a very important note. We will know later why. In part B, here you will find a hole at the middle of the curve or a gap. And this hole or gap or circle means that if we input a to that f of x, the function will not output that height. The function is undefined here. Like for the function that we, just for your knowledge, when we if we graph the x minus 1 over x minus 1, which is simplified into x plus 1, we have to say it's simplified into x plus 1 where x is not equal 1, because in the origin function we have a division by x minus 1 and we need to avoid divide by 0. So if you graph that line at x equals 0, it's 1, and if y is 0, x is negative 1. So this will be the straight line, and corresponding to the 1, we will make a hole, which says that x is not equal to 1. Yes, that's the graph, which is that straight line. This is the x squared minus 1 over x minus 1 versus x. This would be the graph. Okay, so this is considered a discontinuity. They call it discontinuity in the function. That hole or that gap, discontinuity at x equals 1. Because of that example where we might have a hole. Another example of discontinuity, if we have the absolute x minus 2 that we dealt with over x minus 2. If we considered what we did, we said that this is going to be equal to 1 if x is bigger than or equal to, and -1 if x is less than 2. So if we need to graph it in the xy plane, we will just denote starting from 2. We have here 1, and any number bigger than 2, the output is 1. And if the number is less than 2, not 2, before 2, any number before x equal 2, the output will be -1. So here we know that there is a discontinuity that happened to the function at x equals what? 2. There is a jump that happened at x equal 2. So this is another type of discontinuity that we might consider, and these are the two cases that we consider for the discontinuity. That's case number 1, where we have a hole or a gap, and number 2 when we have a jump. So here we have that hole, and it means that the function is undefined here. But if you notice, if we try to evaluate the limit as x approaching from right, will be the same value as x approaching from left. So the limit will exist with a certain value, but the function does not exist here. So f of a is not defined, while the limit exists. Here in part 3, we have that jump behavior. If you address that a from the left, you will find a value, and addressing it from right, you will find a different value, which means there is a jump that happened, and the limit what? Does not exist. The limit from the right is not equal to the limit of the left. But the function itself, if we evaluated f at a, we have here a hole, which means it's not defined, but we have here a circle, that desk, that colored circle. This colored circle means that the function is defined and it will output that height. We go to the y-axis and see the corresponding height. So the function is defined, but the limit does not exist. It's exactly the opposite here, where the function was not defined, but the limit was existing. Here, the third case, if we have a gap and the function is defined elsewhere away of the curve, of the normal curve, we will find that f is defined at x equal a, and the limit also exists at x equal a. From right and left, it's the same value, but they are two different values. They are two different values. So now you can deduce what are the steps we have to do in order to test whether the function is continuous or not. Now you can tell what we are going to do. We will first evaluate the function at that point to see whether the function is defined or not. And then we try to find the limit of f of x as x approaching that point. Sometimes we will have to address from left side separately and from the right side. And then we test whether they are equal or not to consider the fourth case here, where both of them were defined but not equal. And then graphically, in such a graph, we might say that graphically that, for example, here, as x is approaching, what's that value? If you said that's -1, -2, -3, -4, and this is -5. So the limit for that function as x approaching -5, what would it be? From the left, we have that value, right? And from the right, we have that different value. So the limit does not exist. And the function at -5, if we went to -5 and try to find a value for the function, we will find two gaps, two holes. So the function is undefined. Okay, what about -2? Limit of f of x as x approaching -2, here the limit would approach from left to find a value and then approach from right to find the same value. So the limit does exist and is equal to, that's 1, 2, 3, it seems it's like 3.5. Right? And if we want to see the function at x equal 2, we will go at x equal 2 to find the corresponding height. Here it's defined as at 0. So the function also defined, but they are not equal. And as x approaching -1, we have the limit of f of x as x approaching -1, that value. The limit will approach from the left to find a value and then from the right to find another value, and hence it does not exist. What about the function at -1? Here we will try to find the value of the height. Yes, it's here. If that's -1, then this is -2, then the function at -1 is defined at -2. So here the limit does not exist, but the function exists. Here, this is the third case where the function gives that behavior, unlimited behavior. Our point is that approaching from the right is not equal to approaching from the left, so the limit does not exist, while the function itself exists at 0. So it looks like the part 2 here. So now we are considering these three situations in dealing with the continuity of the function. The continuity means it's continuous without an end. It's like the running river. It's continuing without any gap or a hole or a jump. Sometimes they describe it in textbooks. If you start tracing a curve and if you reached a point where you have to put away your pen in order to come back and continue tracing the curve, this is the point of discontinuity. It's described like that in some contexts, and for us we will do that. So here we are asked in exercise 3 to discuss the continuity of the following functions at the given points. We will just discuss the continuity simply at these given points. So here, number A, what's that function? Do you remember when we said if we have x to the power of 99 minus x to the power of 100 plus x to the power of 3 and minus 1 equals 0, as long as the powers of x is positive and whole, then it is what? It's called polynomial. And the polynomial starting from y equal x, that straight line, or y equal x squared, or y equal x cubed, and then power 4 will look like this, power 5 will look like this, and so on, switching. They are defined throughout the whole x-axis. So if we tried to project that curve in the x-axis, it will fill it with these brackets. It will fill the whole x-axis, all of these type of polynomials. In addition to the odd root of any function, in addition to the absolute of any function, their domain is what? Is all real numbers. They are defined everywhere. If you substituted x by any value, you will find its corresponding y with a number. This number can be 0, positive, negative, whole, or fraction, but it is a defined number. So at x equal to, like all the other numbers, this function is continuous. You might add that this is because it's polynomial. That's the reason. Okay, what about number B here? Let's discuss the domain. Because discussing the continuity, we need to know the behavior of the function at different values of x. So here what would happen for the domain? You remember, of course, that we see that there is no root, for example, in the numerator, so the domain is only numbers. There is no root in the denominator, so the domain is only numbers, but there is a fraction, and the fraction cannot accept 0. So we try to factorize this polynomial into, for example, x minus 5 and x minus 2. So we get this factorized form, and we know that this function is the domain is existing for all real numbers except these values, which is 2 and 5. So we subtract them. One might say, I want to say from negative infinity to 2 opened, and then from 2 to 5 opened, and then from 5 to infinity open. Okay, that's all right too. That's totally accepted as well. But if we say that the domain, which is the possible x values where the function is defined, is for all real numbers except for 2 and 5, I will definitely tell you that at x equal 2, f of x is what? Is discontinuous. Because at x equal 2, we will have 4 over 0, because f of 2 is equal to 4 over 0. And if we try to divide by 0 in the calculator, you will find it infinity, or you will find an error. It will give you an error in the calculator. But if you tried 0 over 4, by the way, you will find it 0. So here at x equals 2, the first point that we are asked for, the function is discontinuous, while elsewhere at any other point in the x-axis, this includes the x equals 3, the function f of x is what? Is continuous. It has no problem at x equals 3. Let's see how can we test this for number B. Let's test the continuity at x equal 3. The first step, we will find f of 3. And f of 3 is what? 6 over, here 3 squared, which is 9. 9 minus 27, which is 18, negative 18, plus 10, this is negative 8, so it's 3 over 4 with a negative sign, so it's defined. Let's find the limit of the function as x approaching 3 for the 2x over x squared minus 7x plus 10. It will be as well, by direct substituting, it will be negative 6. Oh wait, it's 3. 6, only 6, yes. So it's negative 3 over 4. So they will be equal, and in the final step, we find that f of 3 is equal to the limit of the f of x. We don't have to write that formula, just denoted by f of x as x approaching 3. Both are equal to negative 3 over 4. Therefore, f of x, this is our conclusion, is continuous at x equals what? 3. This is how we study the continuity at a certain point. Here we discussed the domain, so we excluded the 2, so directly we can say that the function is discontinuous. And also, if we try to pass by these steps, we will find that f of 2 is equal to undefined, which means that the function is directly discontinuous. Let's consider part C, where we have a piecewise function, and we would like to imagine how it works. Here is the 3, which is the joining point. When x is bigger than 3, that's the ruling function. Here, when x is bigger than 3, if x is less than or equal 3, then the ruling function is 1 over 3x minus 2. Okay. Now what do we want to study? We want to study the limit at x equal 3. So let's say at x equal 3, what about f of 3? We will go to the function. Here it says or equal, right? So here we will substitute 3 over 3 is 1 minus 2, which is negative 1. The second step is to find the limit as x approaching 3. 3 here is the joining point in a piecewise function, so I can't approach it at once. I have to approach it from right and then separately from the left, right? Would we substitute the f of x in both sides? From the left, 3 power negative, we will substitute the 1 over 3x minus 2. And from the right, we will substitute it with the negative 2x plus 5. And the first approach is to direct substitute. Here we will have negative 1, and here we will have negative 6 plus 5, which is negative 1. Both are equal. Then finally, what we will do is that we will find that f of 3, which is equal to negative 1, is equal to the limit of the function as x approaching 3 whole in general, which is equal to negative 1 as well. Therefore, f of x is what? Continuous or discontinuous? Is continuous at x equal 3. Let's do the same at x equal 1 because it was required here to do the same for x equals 1. So we will say at x equals 1, first f of 1 is where 1 is less than 3, right? So if 1 is in the left of 3, it will be ruled out with that function. So we will direct substitute here for that x here, which is 1 minus 2, and this will be 1 over 3 minus 2, as if it's 6 over 3, so it's negative 5 over 3. 1 minus 6, negative 5 over 3. What about the limit as x approaching 1? As x approaching 1, which is here, it's not a joining point, right? So we can address it directly. We have one definition in that interval, which is the 1 over 3x minus 2. So of course our first approach is to direct substitute, and by direct substituting we find it negative 5 over 3. And in the last step we are going to test whether they are equal or not. So we will find that f of 1 is equal to the limit of f of x as x approaching 1, which both are equal to negative 5 over 3. Therefore f of x is what? Is continuous at x equals 1, right? So we decided here that x is continuous. The function is continuous at x equal 1, and it's continuous as well at x equal 3. And this is how we show it. Okay, let's move to the last exercise we have here. Yes, to find the intervals for which the following function, that's our last exercise, to find the interval, the intervals for which the function is continuous. So here, let's start for part A, where the function would be continuous, as if it asks us what are the possible x values where they will have, and it's guaranteed to have a corresponding y, not a gap or a hole for the function. We will discuss again the domain. And we will say that the domain for the f of x, which is equal to 5 over x squared plus 1, is all real numbers except in the zeros of the denominator, which is here what? There is none. There is none. We have did this before. If we try to solve x squared plus 1 equals 0, this means that x squared is negative 1, which is a false statement, not true. So it seems that x squared plus 1 is not equal to 0. It will never be equal to 0. So x is equal phi here. And therefore the domain of f is the whole real numbers from negative infinity to infinity. Both are opened. We might indicate opened like a bracket or squared opened bracket. This is both words. So here we don't have any restrictions, so we will say that f of x is continuous along or through R, through all real numbers, which we can denote them by capital R. Just capital R, you don't have to add that bar even. All real numbers. Okay. What about B? B here says it's a function equal to 2 over 1 minus x squared. What about the domain of that function? Here, the domain is all real number and extract the zeros of the denominator. Let's take 1 minus x squared equals 0. This means that x squared is equal to 1. And this means that x is positive and negative 1. So we will exclude the negative and positive 1. You all know when we apply the root on both sides here, the root for something squared which is unknown, that's absolute, equals square root of 1, which is 1. And we solving the absolute in equation, this is x equal 1 or x equal negative 1, right? We all knew this in worksheet 1. That holded a lot of basics. So here we will say that f of x is continuous at x not equal to negative 1 or x not equal to 1. This statement means that, or it holds that, x elsewhere is continuous. So if x is not negative 1 nor 1, f of x is continuous. You don't have to say anything more. So now we have discussed this, and we know that the summary of discontinuity, that it can be removable. We are not asked for the type of discontinuity, so don't care about it. Just know it inside your mind. It's more convenient. If the function is undefined at the curve, so the limit value is different than the function definition, this is discontinuity. If the limit does not exist and the function exists, in that red circle, it's discontinuity. If the limit does not exist and the function does exist, that's a third type which we don't deal with the infinity here. So finally, I would like that you try in this star problem which value of c will make the following function continuous at x equal 2. Just think about it. It's a challenging one, but it's very simple as well. It's beneficial to know that some operations can be applied over the continuous function if f and g are continuous and that c is constant. Then the following functions are also continuous. And when we say continuous, we have to decide at x equals a, at a certain point. We always study continuity at a certain point, not in general. So if f and g both are continuous at x equal a, the f plus g will be continuous as well, and the f minus g will be continuous as well. And any constant times f, if f is continuous at x equal a, any constant times f will be continuous. And the product of the two functions is continuous as well, although the quotient or the division holding that the denominator is not 0. For your notice as well, these are the common types of continuous functions, that they are continuous everywhere in their entire domain, the polynomials for all values of x, the rational functions except the points where x is giving a divide by 0, the root square for all x if n is odd, and if n is even, for x bigger than or equal 0, it has to be positive inside the root. If it's a square root, 8th root, 12th root, any even root. But if it's an odd root, no, it's all real numbers. The trigonometric and inverse trigonometric, the exponential and the logarithmic, which we will discuss in the next tutorial. Thank you so